Hey folks, Todd Coburn with your Aerospace Structure series. This is a live Zoom lecture on Lecture 5 covering the fundamentals of fastener analysis, including shear, tear out, bending, bearing, and net section. Enjoy. Okay, so this lecture is on stresses of fasteners. We've covered normal stresses and we've covered shear stresses. And now we're going to look specifically at the kinds of stresses that occur when we have joints, joined members, splices, and things like this. Joined members that are attached together with fasteners. Make sense? Okay. So let's take a look at some of the checks that we are going to make. If we have a lap splice, for example, two parts attached together with a bolt or line of bolts, or two skins attached together with fasteners, that's what we would call a lap joint, because there's a lap, two pieces lapping over each other and then fastened together. If we have a force transferring, you can see this lower plate is loaded with a force P, and it's reacted out with the other plate. And in order for those two plates not to slip across each other, that fastener is going to pick up load to hold them together. As you can see, this is a very common scenario for industry. This is how it would look from the side and from the top. If we look at the side view, we can see this lower picture, 411C, and if we look at the top of this, it's going to look like this. The top shows us that there's a single fastener attaching these two lap splices. Actually, what could have been shown in that top view is I could have shown a hidden line. Actually, it would have been better to show that. But what I could have shown is a hidden line right here, which basically shows that this lower plate ends right there, but you can't see it without looking through the other part. When we look at a side view, the side view is found by looking from this direction, right? And that's shown right here. We have the force here. It's got to go through this plate. It's got to go through this plate and come out the other side. In the meanwhile, it's going to go through the fasteners. And there's a number of checks we're going to see as we go through this. You can see that this is for our side view. And if we look down from the top, that would be for our top view, which we see down here. You see those two? You understand how those look? Hopefully after our drafting little experience, we're starting to see how that would look. Okay, a quick look at the stress checks. First, we're going to do a net tension check. Basically what that means is we're going to take each plate and we're going to evaluate as if we had cut this member right through here and evaluated the net tension. That will look like this. The next check we're going to be making is a shear tear out check. What that basically does, if you've ever done a hole punch of a piece of paper, right? You take a piece of paper and you put a hole punch, and if that hole is too close to the edge, it rips right out. In fact, if you're right at the edge, it's pre-ripped. So imagine this fastener ripping out through these two planes. That's called shear tear out. We're going to see how to do that. Next, we're going to see a bearing check as that fastener presses against the material. If you have two plates, they're going to slip unless you drop a fastener through there, and then that fastener is going to press against that hole, kind of like this. And that's called bearing, the stress that develops on that surface. And this is how that looks. We're going to look at that next. Then we will look at our fastener shear. If you take a look through here and you see that this is the interface plane and that these two plates would slide on each other if the fastener wasn't present, you can see that we're going to have a little area of the fastener that picks up shear. And that's our fastener shear check. And then lastly, we have bending. Since the lines of action of this force and this force are offset, that induces a little bending moment. The reaction of that is actually rather complicated, and this is a gross simplification, but we will learn how to deal with those kinds of stresses as well. So that's where we're headed today, and these checks are critical for anyone that wants to do structural analysis in aerospace or any other field. You still with me? Okay. All right, so let's walk through each of these in detail. The net tension strength is our first check. And the reason it's our first check is because we have these parts being pulled on, and that's going to develop normal stresses equivalent to P over A. But when we get to the cutout for the fastener, the hole, we're going to get a net stress that we kind of were familiar with from lecture 3 when we dealt with stress concentrations. So if we just focus on one of the plates, like looking at the upper plate here, and we're pulling on one end, and that plate would just move under that force, except that it's got a fastener here that's locking it in place. Do you see that? So if we take a look for that force acting on any cross section, we can take any cross section as we move down through the part. We could take a cross section here. That's going to be, the area will be BT, same area, same area, same area, slightly reduced area. And now we have B minus the diameter times thickness is our area. That's going to be our minimum section. That's where we will do the net stress check. We can understand this better if we cut it through the fastener line here and then take this upper piece and draw a free body diagram. We have the force P, and due to symmetry, we can see that each of these will take part of that force. And if this force is right in the middle and everything else is symmetric, then these two forces will be P over 2. That's the upper piece. If we take the lower piece, we see that that's going to look similar, and that's going to be P over 2. Now we see here, this was P over 2 reacting out here, and nothing's happening at the upper part of the fastener. But then when you pull this P over 2, it runs into the fastener here, and that develops this reactive load. That's how that fastener gets loaded. You've got the fastener, you've got the plate, and when the plate starts to move, it puts a force right there. Do you see that? We're going to deal with this latter part later. Right now, we're just going to focus on the stress here. And so we can take a look. This is our equation. And if we sketch this out, we can see once again that our stress here is going to look like this, right? We have a plate like this. We have a fastener in there. And so we're dealing with, this is P over 2, or total is P, right? You got P over 2 over here and P over 2 over here. So the total on this is just P. And we can see that our net area is just the width, B, minus the diameter of the fastener times the thickness. That's the total net area. This is a net stress. And I'm putting a subscript T just to draw attention to the fact that it is tensile. Okay? So this is our first check, and it's a critical one that needs to be made. Now, we don't always think of making that when we're talking about what's the load in the fastener, but this is one of the things that needs to be checked. This is, once again, it's a net stress. If the holes are interference fit, which means that the fastener does not fit in the hole. There's two ways we get that. One is with rivets. We'll drop a rivet through the hole, and then we'll buck the bottom so that the rivet gets shorter and shorter, and the bottom little tab that sticks out gets pounded into a head. So you've got a fastener head on the top, you've got a deformed head on the bottom, and in between, since this rivet's getting squished, that rivet gets fatter and fatter and fatter and fatter, and it expands the hole. That's what's called an interference fit fastener. It puts a compressive stress around the hole that's really good for fatigue. It hardens it and puts a stress in there that's good for fatigue, and it tends, and therefore when we get a load, and we know when we see a hole, we're likely to get a stress concentration factor. But if that hole is an interference fit hole, the effect of stresses around the hole tends to offset the the stress concentration so that there's a no concentration factor at the hole. They're really good for fatigue. So rivets are really good for fatigue because of that interference that they do to the hole. We'll learn a little bit more about this when we get to Arrow 3271. Another kind is an interference fit fastener that you have to jam or stuff into the hole when the fastener is a little bit bigger than the hole, and it's designed to taper and expand the hole like that, and then the nut tightens it up. That's another way to get an interference fit fastener. Whenever we have an interference fit fastener, then in this idea of neglecting any stress concentration from the hole is a fairly good one. It's commonly done in industry. If we have a clearance fit hole, in reality, most holes are going to be larger than the fasteners. If they weren't, then nothing would ever go in. And so there are standards, and there's a lot, we could have an entire class on this that define just how big that hole needs to be. We have close and very close. This is the class of the hole. Close fasteners, very close fasteners or holes, and then looser holes, right? If you just have a application, you're dropping some bolts and the only thing it takes is tension, you don't need a very tight hole to do that, and they'll use a rather loose tolerance hole. But if you have a joint that's has high shear loading going through it, and if you have a loose fit fastener, it's going to jerk around in there, deform everything, and cause an early failure. Okay, so there's a whole nother study we can do for a long time. We're not going to cover that idea any further. What we need to understand at this point is, whenever we have a hole in a plate like this, we're typically going to look for stress concentration factors, unless we're dealing with fasteners. If we're dealing with fasteners, we're going to pretend that there is no stress concentration factor at the hole unless I ask you for a stress concentration factor at the hole. You got that? Okay. So you can remember back, some of you are thinking, let's see, when we did stress concentration factors, we had a line of holes. They looked like fasteners, and we did calculate stress concentration factors. That is just because it's a practical industry-like example, but typically we are not going to apply stress concentration factors at fasteners. However, if we have low stresses down below the yield, and if we have a loose fit hole, one that's not an interference fit hole, then it's very possible that we would have a stress concentration factor that would need to be evaluated in industry. In this class, we're not going to do it unless requested. Got it? Okay. Let's see. Okay. I think we're on to the next idea. Okay. So once we have, and then I think the last slide also said, we're going to take that peak stress from our net stress, and that gets compared against FTU, right? It's a tensile strength. If it's a tensile stress, then it would be compared to FTU of the material, right, for our margin of safety. Next, we look at a shear tear out stress, okay? Shear tear out is that idea, like that paper. Yeah, yes?
I had a question for the last slide. And
yes.
If the force were to be changed horizontally, how would the net stress at the hole change?
Well, we're looking at this. We're looking at this joint. It doesn't matter whether that's vertical or horizontal.
Okay.
We're talking about the loading goes into the plate, goes through the fastener, and goes out the other plate. Make sense?
Okay. Yeah, so just to be clear, whether it's horizontal or vertically, the net stress at the hole won't change the formula given.
Well, if we have a joint like this, then that formula is valid. If we have a joint like this, then that formula is valid. Is that what you mean?
No, I doesn't necessarily mean
Our joint is like this, then it's valid. If you mean, what about this? We have a part like this and another part like this. Let's say they're joined here with a fastener, and this one's in shear. You may end up with a different check.
it was sort of like that one, but maybe next week when I see you, I'll draw it for you.
Sure. Yeah, if you want to stay on afterwards, we can look at that, or tomorrow in office hours. Okay, so now we're on to shear tear out stress. So basically this part is going to look like this. Remember, we have the part loaded like this. We're looking at the upper plate here. We see that we have a force applied P and it's being reacted. Now we've already verified that it can get, right, the first place this thing can fail if we cut it right here and right here. We verified the load can get past that point without failure in our last check, our net tension check. And so we're now ready to move to our next check. And to do that, we're going to take a little close look. So let's go ahead now. Imagine the force got through there. And let's look at what happens next. Let's go ahead and make a section cut right there and right there. You see that? The force got around. This is what we see now. So this force came around this side and it came around this side. And now in order to load this fastener, right, it's not pulling on the fastener up along here and it's not shearing into the fastener from over here. They're not attached. So the load now has to go through here and get into this material behind the fastener before the fastener can get loaded. Just like your paper with a hole, if you have something going here and you pull on that, once the load gets around, it now tries to rip this little piece from the material. And what happens is, if we focus on that, we see, well, let's draw a free body diagram of the other piece. So what we see now is we have this part and we had a hole, right? We have a force here, P. And actually what that means is we're going to develop, and this is where our hole was, we're going to develop, this is P. So this is going to be P over 2, and this is going to be P over 2. Do you see that? This force is reacted by this part that we had to cut it here, and we had to cut it here, there and there. So that means these two forces are P over 2. Now, if we just focus instead on this little piece in here that we cut away, we see that the distance from the center of the hole to the edge of the part, we're going to call that E. And that E is what we call edge distance. What is E? It's the distance from the center of the fastener to the edge of the part. We have an edge distance in that longitudinal direction. We also have an edge distance in this other direction. We're not going to worry about that right now. We're just going to look at this one here. And that's the distance from here to here. That's the distance from here to here. Do you see that? So actually, since this force causes these two reactions, P over 2, that means that we're getting this is poorly drawn. These should both be up, right? Up and up. What that means is this part here is trying to pull this way, which is putting a force here, and it's reacted because the fastener's here. Now, when that little piece of material tries to move forward, it's stopped by the fastener. You
so
see that?
Professor, we have shear stress right there, right?
And that is, well, if you look at this, this is a force. Is that force parallel or perpendicular to that area?
That's parallel.
It's parallel, so it's a shear force. You can take a point for that. If we draw this in 3 dimension, take a look at this. Here's our little piece that we removed from the material. And if we look at the thickness, we see it goes like this, right? We got a fancy little area there. This little area here is E, right? That edge distance times T. And over here, this is what that movie is all about, E.T. Phone Home. They were trying to do this kind of stress check. We got a force acting on that like this. And we also have a force acting on this. So actually we have this force, P over 2, acting on ET over here. And we have P over 2 acting on ET over here. So we can say the shear stress on this face is P over 2 over ET, We can say that the shear stress on this face is P over 2 over ET. Or we could say that the total force P is acting on an area of ET plus ET, which is 2 ET. These are all saying the same thing. You see that? Either way, we slice it. You've ever heard there are many ways to skin a cat, and everybody that says that has never skinned a cat, right? You can take out that stuff from here. You can take it out, cut them along the crotch and take them out from that end if you're going to mount their head. There are a bunch of ways to skin a cat, and there are a bunch of ways to evaluate our shear stress. Don't worry, skinning a cat will not be on the exam. There are many ways to feed a dead horse. I guess there are.
We get extra credit if we mention skinning a cat on the exam.
I'm sorry, one more time.
I said, will we get extra credit if we mention skinning a cat on the exam?
You know, you get extra credit for a lot of things in my class. I've given extra credit for playing Dungeons and Dragons, for wearing cool looking boots, for answering questions. If I get too far afield in my tangents, if I'm late or if I go over. So certainly it is possible. It is possible. And I have had clever, laughable comments on tests and homeworks that I have given extra credit for. I'm not real consistent because it all depends on the moment, right? My goal, I have certain things that I apply consistently, and there are other things that are designed to reward you guys for being you and for thinking well.
Professor,
Makes sense?
is this lecture also going to be in the exam?
Is this lecture going to be in the exam? What does the
Does
syllabus
the
say?
syllabus
I think
says
the
1 through
syllabus,
4?
yeah, the syllabus doesn't include this lecture.
Lectures 1 through 4. Yeah. Usually I won't put, I rarely will put, except, I think except for the last lecture of the class, usually I won't put a lecture from the immediate prior work unless we've had a chance to do the homework and get that homework turned in and ask questions about it. The only time that will be off is sometimes with holidays or with the last test. And so you'll see those exceptions, but you almost always, I don't do that. That answer your question? Okay.
Yes, thank you.
So you guys got this. So this is how we evaluate this. So our stress then, as we showed, is P over A, which in this case is P over 2ET. Why? Because the total force is P and the total shear area is 2ET. Another way of thinking about that is we have the total force is P over 2 acting on one area of ET, which gives us the exact same formula. This is called the shear tear out stress. It's the one that yanks that out of the part. Now, in not only aerospace, but in many industries, a common rule of thumb is that we will put a fastener, it needs to be at least twice the diameter from the edge. And that means more than twice the diameter, not twice the diameter, because what happens is it's never perfectly placed. And if somebody ends up making a mistake, they may have to oversize the fastener to the next size up, like a 64th larger diameter fastener, and that will violate that. So usually it'll be that twice the diameter plus a little bit of margin, maybe a 32nd or a 64th or even a little more distance away. And any design that's made where the fasteners have an edge distance of twice the diameter or more, and then as just for your knowledge, a common rule of thumb for spacing of fasteners is 4 times the diameter. So the edge distance, twice the diameter, spacing should be 4 times the diameter. It's common in industry to design those to 4 to 6 times the diameter, but 4 is the minimum that should be seen, and the edge distance should be 2 or more. Okay, if our joints are designed to that practice, then it is rare that you will have a problem with shear tear out. And for this reason, shear tear out is often not done in industry. The times when it is done is if we have a short edge distance condition. Now, Mill Handbook has allowables for shear tear out, and our handbook does. In the appendix, you'll find FBRU. So we're going to talk about bearing in a minute, but FBRU is what we use to check our bearing strengths again. And this is for an edge distance, E over D ratio of 2.0 or more. If our edge distance is 2, then the ratio of the edge distance to the diameter is 2. So this is the allowable we're going to use for bearing, as we're going to see in just a minute. And as long as our edge distance is equal to or greater than 2, you mostly won't have to check tear out. It's when our edge distance is less than that we ought to check it. And that's where I see where my clients and others will evaluate a shear tear out check to make sure that we're not so close to the edge that we rip that part out. And the reason we can neglect it when our edge distance is 2 is because they've already done a lot of tests on these. They know what the allowable is for edge distances like that. And those joints have been designed not to fail and tear out. You guys with me? So for our class, if I ask you to do a shear tear out check, I'm going to expect you to do it correctly and to use this approach. However, if I don't ask for a shear tear out check, you mostly won't have to check it. You'll mostly be checking bearing and shear stress on the fastener, and sometimes net tension. Got it? Okay. So that is how we do shear tear out. This is a common one that students often mess up. They struggle with this idea. They'll either calculate P over ET or P over 2ET or P over 4ET with no apparent understanding of when which is used. But if you understand what I said about figuring out what's the force on the area and what's the area, then this is a very simple check to make. Got it? Well, one thing I'm not showing on this slide is this is a shear stress. So what do you think you will check this against?
Would you check it
you'll
against
check-
FSU?
Yeah, baby, FSU. Point. Got it? Okay, FSU of what? FSU of the plate. What if your two plates have different FSUs? You check it against the minimum one, whichever one gives you a more critical margin of safety. Okay, next idea. Now we looked at shear tear out in lap splices. Let's say we have a butt splice. What's a butt splice? We got two parts. Now the other one, we lapped them over, right? We took one plate, we took another plate, we lapped them over, and then we fasten them together, right? This is how most, many or most skin splices are done now in industry because they're cheaper than the ones that are better. A butt splice tends to be a better design. With a butt splice, you're going to take two plates and you're going to butt them together. Now they're not attached. So what you're going to do is take another member over the top and attach it, and another member under the bottom, and then you'll fasten those together. Now we see this plate is being pulled on here, and this plate over here is reacting that. But in order for that load to be taken, the load has to come out of here into these two splice plates, go down these splice plates, go back through that fastener and over. I've found that students really struggle with this concept. It's actually quite simple. You need to make sure you spend enough time understanding how this works, okay? So this is a butt splice, and that's how a butt splice works, as opposed to the lap splice that we saw before. Now, if we have a butt splice, here's what happens. And this is a blow up of this leftmost plate. So if we take a look at this plate and blow it up and remove everything else, you'll see we've got a force P acting here. Okay, that's the same. And now we're making a section cut right through the fastener there. You can see that. That's where we would have done that net tension area. This is our central plate. So this total force is in this plate. And that means, what is the force acting on this fastener in this plate? It's the total P. Do you see that? So that means our net tension in this plate will be P over this area, D minus, or B minus DT. Then we're going to have a shear tear out. That is, our shear tear out check is going to be P over 2ET, right? These two areas. Our V is just P over 2. And then we're going to have a bearing in the fastener That's going to be, and we haven't covered that yet. We'll cover that next, but then we'd have a bearing in the fastener check, and then we'd have a shear in the fastener check. We'll deal with that in a minute. Okay. Now, once the force gets into the fastener, you'll notice this upper plate. If you look at this part of the plate here, you see, remember, this is P, but if you take a cross section here, like let's just say we draw this lower plate, and that's being pulled on with P, and it looks like this. But then we have another plate like this, and we rip it right through the middle here, right? So this is the upper plate, and we have a lower plate down here. So that means that this is P. Now you'll notice this plate ended, and this other plate over here hasn't started yet. That means this is P over 2, and this is P over 2. This is so simple as to be laughable, but students commonly miss that. How do you figure that out? Well, if we draw this from the side, oh, that messed that up. Let's do it this way. Here's our splice plate on the top. There's our middle plate. Here's our middle plate. You'll notice these two plates are not attached directly. The load has to go through the top and the bottom. If you cut it through here, right, you see, and then say, all right, if we cut it through there, then we can erase this other, oh, that's not going to erase the thing we want. Then that means that if this is P, that means if this is P, then that means this right through the middle of this plate is P over 2, and this is P over 2. This first fastener takes the whole force, and it actually carries part of it up here and part of it down here. Do you see that?
Professor.
So when we look at this plate here, 1 second, when we look at this plate here, we see that that force, this is P over 2 that this picks up. We're getting P over 2 acting on this surface. That means the tear out in this plate is a force of P over 2 divided by 2 ET. Now this was total P over 2 ET, but the T we're dealing with is the central plate. Up here we have P over 2 acting on this one, and this is 2 ET, but the T here we're dealing with is the upper plate. Down here we're going to have a shear stress equal to P over 2 ET, but the T here is now in the lower plate. And this E is actually in the upper plate, and this E down here is in the lower plate, and this E is in the central plate. They might be the same edge distance, they might be different. You see that? You guys understand that? It's critical. Then when to go on, that means this force comes here net in the central plate, net stress, and then we've got that tear out, and down here we've got P over 2 and that tear out, and P over 2 and that tear out. It's critical understanding this not only for tear out, but also for the material that's coming next. Got it? Okay. Yes, Mr.
Yeah. So I was going to ask you, the maximum stress in that part is going to be on the plate, or it's going to be on the tear out part?
One more time.
The maximum stress. Where is it going to be in that system?
Who knows?
Okay.
Who knows? So sometimes we'll be able to look at the part and know immediately. Like let's say the central plate is the same thickness as our upper and lower splice plates. In that case, that central plate is the same thickness, it's carrying more load, that's probably going to be critical.
Right.
But if a lot of times those splice plates will be thinner, right? Like half the thickness, in which case they might be critical. Often they'll be the same material. They might be a different material. Maybe they're weaker, or maybe they're stronger. Maybe those are steel and the other part's aluminum. So if you have the judgment and experience to quickly spot what's critical, then only analyze that. Unless asked otherwise. But in industry, you've got to figure it out. And if you can't tell which is critical, what do you think you should do?
Calculate.
Yes, calculate. Check everything.
Right.
Start with the central plate, you do your net tension, then you do your tear out, then you do your bearing, then you do your shear. Then you go to the upper splice plate and you check The way that comes in, that will be shear, then bearing, then tear out, then net tension. And then the lower splice plate, shear, then bearing, then tear out, then tension. And if all that shows good, then you're home free. And
Right.
you report your minimum margin of safety.
Professor.
Okay.
Yeah.
So the order that we check it in, we just go in the order that the force transfers throughout everything.
Sure. So you can actually check it in any order. But
Okay.
in my handbook and in my lectures, I'm trying to be more and more systematic, and it's easier to keep track if you just trace the load through and make every check as you get to it. Okay. As I said, the two checks we're going to make are bearing, we haven't covered that yet, and shear. The checks we will sometimes make are net tension and shear tear out. Okay. Okay, here's bearing stress. Once again, we're dealing with the same lap splice. And what happens now, once you get the load, you've shown that the load can get there through net tension, and then you showed that it's not going to shear tear out. And now you get that fastener pressing against the hole in the part. And this is how that looks. If we have this, you can see we got each plate, and it's trying to move under the action of the force, but there's a fastener in the way. So what happens is that fastener is pressing against this area. Now, actually, so you can see in this first little picture, we see how that fastener is pressing and putting a force. If we sum our forces, we see P minus P equals 0. We've got equilibrium. So that's how you calculate your force. In fact, there's going to be a nonlinear distribution of stress. As tunneling would be more like, tunneling would be different. It's like if we take a sheet and lay one of you in the middle of the sheet, me and Mr. Rouse grab the sheet and we're laying the person, and that sheet is pressing against one side of the person. Or if we have two large plates with a man-sized hole, and then we drop a student through the hole, and then we try and move the two plates. That's what we're talking about, how that plate bears against the person, okay? And the stress distribution is not linear at all. It looks something like this. But actually, that's too complicated for the average stress analyst, and we can do it more simply. So we're going to make a gross simplification. Are you ready for this? This is our simplified bearing model. We're going to look at the projected area of the hole. We're going to pretend that the area of contact is that projected area, and we're going to calculate our stress P over A as if that projected area were a real thing, like as if it was a slot rather than a hole.
So that would be an average bearing stress?
It is an average bearing stress point. Yes, Francisco. So our P in this case is the full force. The area is going to be that projected area, which is diameter times thickness. So P over dt. Got it? P over dt. That's how that looks. All right. If we look at that a little closer, we see it's kind of like we have that bearing area. Here's a fastener on the upper plates pushing one way and the lower plates pushing the other way. Both plates pick up this bearing. First, it picks up in the one plate. Let's say we start the other picture, we were looking at the top, right? So this one picks up the bearing, and then it's going to run down. The force is going to run down the fastener, and then the other plate is going to be picking up the bearing in the other direction. That's how that force transfers. And so you can look at this set of pictures for what happens in the plate, and this set of pictures to see what happens on the fastener. Got it? Okay. Our bearing stress then is just P over dt. This is called bearing stress. We're going to, it's based on that. We already said that. when we do allowable testing, we're going to actually put fasteners in and pull these parts apart. We're going to evaluate what stress it fails at, but we're going to use the same calculation procedure to calculate those stresses. Therefore, the bearing allowables are based on the same model. And this is why we can make these gross simplifications and actually be conservative and correct. Got it? And we're going to check our bearing stress against FBRU. Okay, word of warning. FBRU in the back of the book, you're going to see two values. So we often will call this, we could just call it F, but we're going to call the bearing stress FBRG for bearing for obvious reasons. When we look at our allowable, it's going to be FBRU. In Mill Handbook, there's also an FBRY, which we're not going to ever use in this class. And I'm always a little disgusted when folks in industry use it, usually by a lack of experience. There isn't a special cases when we would use that. We're not ever going to use that, so I didn't even put it in your book. You're going to notice, though, that the FBRU values in the book, you got two values. You've got one for E over D of 2 and one for E over D of 1.5. That means E over D equals those. And E over D of 2 means that your edge distance is 2 times the diameter. That means it's been designed to good practice. If you have less, that means you're probably dealing with repair or somebody that didn't know what they were doing or something else went wrong. Okay? Since you have both values, what that does, anytime our edge distance, our E over D ratio is 2.0 or more, we're going to use that 2.0 value. We're never going to increase that, but we're going to use that value. Whenever our edge distance is less, if it's between 1.5, if our E over D ratio is between 1.5 and 2.0, we can interpolate for the allowable based on what edge distance we have. You got it? If our edge distance is ever less, and often we will check shear tear out if we're anywhere between these two, although really you shouldn't have to as long as you're above 1.5. If your edge distance is ever lower than 1.5, that's when you're going to have to do something fancy for bearing, and then you should also check shear tear out because it's very possible that there's not enough shear area to develop the full bearing allowable anymore. You guys understand that idea? Okay. So, but in our class, are you listening to me? All we're going to use is, we're always going to assume a 2.0 edge distance. So we're going to use the bearing allowables for E over D ratios of 2.0. We're never going to do any interpolating in this class, and we're never going to use the 1.5 value. That is there because if you start an internship or start working in industry, you should be aware of a value you can use if you're outside that 2.0 limit and how to use it, but we're not going to cover it. We got our hands full already. Okay.
And what's the difference with this BRG value instead?
I'm sorry?
And this is different from BRG?
FBRG is our calculated stress. We have a force. It's based on ultimate loads, and this is the stress associated with it. And we might put a subscript BRG just to remind us that it's bearing. When we go and we calculate a margin of safety, we're going to need to first find the allowable. That would be our FBRU, right? So our margin of safety it's always the allowable over the calculated. That's FBRU divided by the stress FBRG minus 1. What do you think the U is for?
Ultimate.
Ultimate.
Means it's an ultimate allowable. So this is how we show that it's a bearing allowable ultimate, and this is how we show that it's just a bearing calculation. We could have just said F equals P over DT. It's obvious that it's a bearing stress. It's just like saying, you know, Edward is a student in my class, but there might be an Edward that's a professor. But if we're in my class, we're realizing it's obvious that it's Edward. We could say the student Edward is a student or something. We put a little subscript here that name is associated with a student in this case. In the same way, That BRG just saying this is a bearing calculation, and it gets compared to a bearing, ultimate bearing allowable. Does that answer your question? Okay,
Yes, thank you.
you're welcome. All right, so that is our bearing stresses. One other comment. So bearing stresses act on both plates, right? They're acting on the upper plate and the lower plate. But if they're the same thickness, usually we'll just check one because that covers both. If we have two different thickness plates, which one do you think is more critical? The thinner one. If we have two plates with different materials, which one do you think is critical? The one with the lower bearing allowable. If you have two different plates, two different materials, and they're different thicknesses, then it's hard to tell by glancing unless the thinner plate is also the weaker plate. If the thinner plate is the stronger plate, like we got a thin steel plate attached to a thick aluminum plate, then we would need to check both to be sure that we're good. Make sense? Okay. So we've got, that is how we handle. Dylan, did you have a question?
Yeah, I had a quick question. Is the diameter that we're using, is it the diameter hole or the diameter of fastener? Because if the fastener is really small, wouldn't the area that's pushing out just be the contact between the small fastener?
Yeah, good question. So basically in our class and for almost all industry analysis, we're going to assume that the hole and the fastener are the exact same diameter. And we're going to use the nominal diameter for that. In fact, if we have a 1/4 inch fastener, the fastener isn't a 1/4 inch at all. It's something just less. And in fact, if we have a 1/4 inch hole, the hole ain't a 1/4 inch, it's something just more. And a proper drawing will actually have a tolerance specified that the hole can be, it's got to be a prescribed amount larger plus something, but not minus. And a fastener will usually have two limits, both of which are smaller than the nominal size. But to carry all those digits is to add a lot of complexity and a lot of detail and a lot of confusion. So what we will do is treat both as the nominal for most calculations. So if you have a 3/4 inch hole, we're going to do that. We're just going to ask ourselves, is this an interference fit hole or not? If it's not an interference fit hole, we might need to also look at stress concentration for our net stress. Although, as I said, in this class, you won't check for the net stress unless I ask you specifically, right? Or unless I ask you which strength checks need to be made. Boom, yes, that also needs to be made, right? You need to understand that. If I ask you for the critical margin of a joint, I could be asking for all of them, but often when I ask that kind of question, I'm just looking for that trade-off between bearing and shear, which we covered bearing, we still haven't covered shear.
Okay.
Make sense? All right. Okay. So that is how we do bearing stresses. We already said that also. Okay. Next, our shear stress. Okay. So we've gotten the load through the net section. We've shown that it's not going to tear out. We then showed that the bearing was sufficient to transfer the load. And now we get to checking the actual fastener for shear. Here's how it works. You can see we've got these two plates moving like this. And the line of action of the force, that force is basically going to be running down the mid plane or the centroid of the upper plate. And it's going to be running down the mid plane of the centroid of the lower plate. And you'll notice these are not the same position. It's not possible. Therefore, we get an eccentricity between those forces. Do you see that? Now, we're going to actually deal with this on the next slide. But when we're doing shear checking a fastener, we're going to ignore this eccentricity and pretend that it's zero. That actually is true, or fairly true. Let's say we have a plate, it's relatively thick. You can see we're going to get a significant eccentricity between these two, right? But as these plates get thinner and thinner, this eccentricity gets smaller and smaller and smaller. In the extreme, you have an infinitesimal plate being pulled this way and an infinitesimal plate being pulled this way. And they're basically, the eccentricity between them is close to zero. In that case, you could see that the only thing in, no matter whether you have an eccentricity or not, you can see, imagine having, how many guys have ever used a hacksaw before, right? Little thin blade. How many guys have ever taken your hacksaw blade out, grabbed it with your hand and sawed through something? And when you're done, your hand works like this, right? For about 40 minutes. Yeah, I've done that a number of times. Imagine doing that. Grab your hacksaw and slip it right between these two plates and cut that fastener. When you're done, you're going to have a lower fastener that looks like this and an upper fastener that looks like that. You see that? And if you look at this, you see this area is what you cut through. And if these two plates try to slip, then basically what you're going to do is get a force P that's reacted by a force P. Therefore, the stress is going to be P over A. What is the area? Right? And since fasteners are usually not called out by radius, they're called out by diameter. It's P over pi d over 2 squared, right? That is our shear stress. And basically what that assumes is that the line of action between the two loads is negligible. So our shear stress is just P over A, which is that. Got it? What do you think we check this stress against?
FSU.
FSU. Okay. So excellent. So what happens is we can calculate, we can say, okay, what is the force? We can then calculate a stress. We then look for this fastener, what is the material? And therefore, what is the FSU? And we can write our margin of safety as FSU of the fastener divided by FS of the fastener minus 1. Got it? Okay. Now, a lot of fasteners, now we're not going to deal with this much in this class, although sometimes I'll give you this. When you get to 3271, we're going to do a lot more with this. But a lot of times what you'll do is you'll look up the fastener, and a lot of times fasteners will have published shear allowables and tension allowables. And these allowables are in pounds. When that's the case, we have the shear allowable. I call this P allowable, and I call this S allowable. A lot of times we used to use F for forces, but now we're using P's for forces because F has got that special connotation of allowable stress. S is a value I like to use for force when it applies to force allowable forces, especially for fasteners. So S allowable is a allowable, but it's a force allowable. So you look that up and you say, oh, it's 5,320 pounds of allowable. S allowable is that, or an S allowable for a weak rivet might be about 500 pounds or maybe 200 pounds, right? If you have the allowable of the fastener, you don't need to calculate the stress. All you do is you take what's the force in the fastener and shear against the allowable, and now your margin of safety is simply S allowable of the fastener divided by S on the fastener, that shear force minus 1. What is the shear force on this fastener? P. What is the shear force on this fastener? P. What is the shear force on this fastener? If we have a, remember our double shear, our butt splice with double shear application? In this case,
over
you
2.
can, exactly, P over 2. You can see you need to use your hacksaw twice. This P is going to be reacted here, P over 2, P over 2. So now the actual force is S is P over 2, and the allowable is whatever the allowable fasteners. Okay, we're going to actually see this on another slide.
So, Professor, if you remove either the top or bottom plate, just leave one, the full force will be transferred to that single plate, correct?
Yeah, if let's say we have you're talking about a butt splice that's poorly designed, and we only have one splice plate. Is that what you're talking about?
Yeah, exactly.
Yeah. So in this case, now this is just like a lap splice. It's like 2 lap splices in a row. And you're going to end up getting bending in this plate that you're going to need to check, plus some other effects. This is rarely done. Usually if they use a butt splice, they would have it back-to-back splice plates. They use a lot of these. Back in the 90s, I was working on the MDXX, and they tasked me. I was still a young buck, but they put me in charge of the nose, and they tasked me with cutting the cost by a factor of 2. Alenia had just agreed to build the nose for 1/2 of what McDonnell Douglas was building it for. And they wanted me to cut the cost by another 1/2. And Alenia had agreed to build it for 1/2, but they had no idea how they were going to do that. So I had my work cut out for me. So I told them, well, fine, give me a 1/2 Italian guys from Italy, from Alenia, 1/2 Boeing folks. We'll work together and come up with design changes. At that time, we had splices like this, but even better, we had what's called a finger doubler. So if you had 2 skins coming together, we'd put a splice plate. But then with the splice plate, what we do is have it looks like fingers of the splice. And so you've got a couple, 2 or 3 rows of fasteners here, and then you have fasteners going into this little finger, and then this bulbing out, and it'd be on both sides, like little frog fingers. This thing is amazing for fatigue. They last forever. And yet we're trying to be competitive, and we're switching to lap splices. And I remember we were pitching that, and it was a big savings of cost. And one of our old timers said, we're not doing that because fees are better. I said, well, I agree they're better, but we're tasked with cutting the cost. And we need to do this in order to be cost effective. He goes, we owe it to our customers to do it right. Now, I kind of agree with that thinking a lot. I said, you know, we ain't going to be doing our customers any good when we're out of business because we're too expensive and they're buying lap splices from Boeing and Airbus. Sure enough, within 2 months, they canceled our program for a number of reasons. Part of it was this kind of thinking. It is great to design in amazingness beyond what everybody else is doing. However, when you do that, you have to keep an eye on the financial cost. You need to meet requirements, and then you want to do it as much better as you can and still remain cost effective. If you get too far off that balance point, doing it so much better or different than everybody else that it's more expensive, chances are you will not remain in business to give your customers the opportunity to benefit from your high ethical back fiber, right? So, and it's actually not quite ethics. It's just kind of like a commitment to quality, right? If you've ever known somebody that's clean, right? Like if you marry a spouse who's clean, right? It's kind of nice. The house is always nice and neat. But if they're too anal about it, it can be miserable to live with them if you can't even set something down for 5 minutes, right? So there's a balance point. In the same way with engineering, we have to balance greatness against what we can do cost effectively and what the requirements are and what else is doing. Does that make any sense? Okay. Let's see if there's anything good in the chat. Okay. Yeah, right. Some of you actually, yeah. Okay. So I'm going to erase this stuff on the slide. So that's how we do shear stresses. Okay. One comment on shear versus single versus double shear. This is the single shear joint we've been looking at, and this is the double shear joint we were looking at. We have to be a little careful here when we're doing this to trace our load through. You'll notice here what I did is I took a little cut right through there, and I'm focused on this piece here, and that's what we're looking at down here, right? And we're focused, and I didn't actually complete this picture, but we've got these forces pulling here, and it's actually being reacted by this piece here, right? This force, when this thing pulls, it's applying this being reacted here, which gets placed on the fastener here, gets reacted here and here. And that's where we have this P comes into these plates, which then goes across and then comes down in the same manner. Here, splits, now we're P over 2, and then we're back to coming together again. So this bearing, tear out, and net section are all against P. Our shear is against P over 2. Our bearing in the upper plate and lower plate is P over 2, as is our tear out and the net tension in that member. And then back out the same way. Got it? Okay. And here's how that fastener looks. You can see that P is being reacted by these two V's. What's the magnitude of these V's? P over 2. It looks like I'm belaboring this. Have you noticed yet? Actually, I think my 3271 class is noticing it. I warned them in every lecture we had about all the places students make mistakes. Not all the places, but many of the places where the students make the most common mistakes. And then they went, even after swearing to me they weren't going to make those mistakes, they made the exact same mistakes on their exams. Don't do it. If I'm warning you, it's because I've seen it so many times. And if I warn you for something about 12 times, the chances are if you do that mistake, I'm liable to be very unsympathetic with my points. Make sense? Okay. All right. Here's the next idea, and this is fastener bending, okay? Now, let's take a look at this again. Remember, if we have any forces, if these two forces were actually, remember as we shrink those plates down more and more and more, eventually it gets to be like we have no eccentricity at all. But if those plates have any real thickness, there's going to be a little eccentricity, and it's going to get larger and larger as the thickness of the plates get bigger. We can take a look at this by looking at the two lines of action of the force. Are you with me? It's critical. Right through the middle of those two plates, you see that distance? That's the eccentricity. Okay, now don't be confused. We used E for shear tear out. That's a different E. This is eccentricity, not edge distance. Got it? Okay. So our moment between these two lines of action is actually PE. And that E, actually, you can see that it's half the thickness of the upper plate plus half the thickness of the lower plate, as we see here. Okay. Now the way that actually, and that's going to actually cause these two forces on the fastener on the bolt to be offset. And then the fastener is going to have to react it out with a weird, this is grossly simplified, but this is one way of reacting that load out in a simple manner. We're not going to do any of this in our class. In fact, we're going to do very little bending of fasteners. I'm going to tell you why in a minute. But you should be aware that this actually can develop. So our edge, our eccentricity is T over 2 plus T over 2. If it's the same thickness, then it's just T, right? But if they're different thicknesses, they can be different. That's the moment. That moment is occurring in what? It's occurring in the bolt. So now if we need to check that, we will check that against the bolt bending. And then we need to remind ourselves of cross-sectional areas. Now, in your handbook, in the appendix, I think it's Appendix A, you have some properties of sections. And it's got some circular properties. It doesn't have, you're not going to need this one for area, but you will need the one for I. I recommend writing that formula in your handbook so you have that handy when you're calculating the stresses on a round section. If we have that bolt and if that bending moment is acting in it, then we're going to be getting a stress like that. Our fastener bending is just MC over I, which we can write this way or this way. Now, actually, I'm covering all of this because we're in the fastener section. However, we haven't covered bending stresses yet, okay? So all of this is really not going to hit us at least until after lecture 6 when we cover bending, okay? Or lecture, maybe it's 9. Lecture 9, excuse me, okay? So we're not going to do this for a while, and actually, we're not going to do this at all this semester. Next semester, we're going to be doing this, and I'm going to expect you to have remembered this and mastered it. Got it? But we're not really going to do much with this. You just need to be aware that we can get bending, and this is the moment we would get. You guys need to be able to calculate this, although I can't think of any problems that I've given on this yet in this class. And eventually we will need to be able to also calculate the bending stress in the fastener. You got that? Okay, so why are we not going to have you calculate bending in the fastener this semester? Well, here's why. This is the bending stress. In order to develop this bending, these parts have to deform considerably. Let's imagine we have two plates and we have these two forces acting like this. And let's say that the plates are rigid. They're so rigid they don't deform at all. In that case, you'll notice when you pull this, that little bolt is going to kind of do this, and you're actually going to cheat. That line of action is going to come closer and closer together as if the load transfers right here with like negligible eccentricity. A lot of these loads are going to transfer like that, and therefore the bending moment is usually less than what we would predict with this formula. This formula is a bit conservative. And for this reason, in industry, this check is usually not made. Are you with me? Why? Because a lot of times we're dealing with really thin skins. Now, there are exceptions. Let me give you a quick exception. When I was on the Delta rocket program, I was the lead for most of the composite structure of the Delta IV at that time. And we had a number of guys do an analysis, and the thermal shield, which is on the back end of the rocket. So if you look at the rocket, it's like this, right? You got the fairing with the payload up here. You got the second stage and the first stage, and then you got the engines down here. And then you got your thermal shield right here before you. And this was a big old structure. It was made of composite sand, which was like 1 inch thick. And then what we did is we bolted that to big, huge aluminum fittings like this. So actually the distance between here and here was huge, like an inch or something. And we were a week before launch, something like a week before launch. We had already flown successfully once. Our first flight was already a success. And I had just, because I was the lead for all this structure, I was kind of becoming a bottleneck. There was so much work being done, but I had these great people on my team. So I said, look, I'm resigning as the lead. I'm going to give one guy that was in St. Louis, I gave him the thermal shield. I gave another gal in St. Louis the center body. I gave some other people, Jacqueline in our group, the lock skirt and so on. And I said, okay, you guys are gonna be responsible for these structures. So now we're like a week before launch, and Stefan comes to me and he says, hey, I was checking over the analysis before launch, and I realized this knucklehead job shopper that we hired that did all of the analysis for these joints only checked it for shear of the bolt. He didn't check anything else. He didn't check bending in the fastener. I'm like, oh my gosh, crap. This is really thick. We should probably check bending in the fastener for that. He goes, I know. I said, why don't you check it? He goes, I did. Everything's negative. And they're really negative margins. I said, oh my gosh. I said, well, do it like this. And he goes, that shows negative. I said, well, okay. Well, if we do this, we assume this, we do it like this, we assume this comes like this, this deforms like this, then we do this with the bend and rack that out. He goes, what? So I sketched it out on a napkin. I said, tell you what, I'll write it up for you. So I sketched out a little analysis procedure that looked at how that fastener moved and cheated that load and cheated our bearing area down to like just the minimum we needed with the FBRU to show good. So all of our bearing margins by definition were set to 0. And then we did the analysis on that. I said, and then I emailed it to him. I said, reanalyze everything with this. He goes, okay. So he made this spreadsheet. It was a huge spreadsheet, very difficult to read, but actually it showed all margins of safety positive. All of our bearing margins are 0, but our bending margins now are really tiny positive margins. I said, fine. Now we just got to sell it. So then we put together a presentation. I sold it to NASA. Actually, there's more to the story. But The point is, bending is usually neglected when we have thin skins, thin members being joined. But if our members are very thick, we probably need to evaluate bending in the fastener. In this class, you just need to be aware of that. And if I ask you to calculate the bending moment due to a joint, you need to be able to calculate that. Later, after we learn about bending, I will let you know. I might have you actually calculate the stress as well. We're not going to do that yet. Are you with me? Okay, that's how we're going to handle that. So you're going to be aware that that develops, and also be aware that we usually neglect it, but that may not be the best approach for all design. Okay. Here's another little bearing. Now we saw a very specific meaning for what the bearing stress means, but let's look at a different thing. Let's say that you're designing your patio and you have a post that's sitting on a concrete slab that's sitting on the earth. You can see that means you're going to get a force acting down on this post. And the stress on that, that's a normal stress, is just P over A. So typically we would just compare that to FCU of the material. And that's valid for a member like this with known dimensions. Once you get down into this other member though, you still have that same compressive force. You can see the stress in this 4x4 is this, yes, but the stress acting on the plate down at this area has the same area and the stress is the same, P over A, but now that compression is not on a piece that's, it's got that area there, but you'll notice if you look down, if we look at a side view, we got the plate here, and then we got the earth, you'll notice, although that's the area right here, if you go down just below the surface, the area is much larger. And then if you look at the area here, how this plate presses on the earth, you've got a larger area. It's now W by W area, but it gets immediately larger once you get in. When you have a structure like this, then the appropriate check is actually P over A, yes, but what you will check to is we would check this against FCU, but these two would be checked against bearing allowables, FBRU. This would be checked against the bearing allowable of concrete if we have it, and this would be checked against the bearing allowable of soil if we have it. You see that? So even though it's not bearing in the sense of how we deal with that fastener bearing, we can use that those bearing allowables for fasteners is a more appropriate compression check for these kind of members. Okay. I mainly just want to alert you to that. There's a homework problem where you're actually going to do that kind of thing, and I'm going to expect you to kind of understand that and be able to implement it, although we're not going to go real deep on that. And this slide talks about it, in your handbook talks about that special case a little bit. You guys with me? Okay. These are some other things we're going to cover, but not this semester. When we get to 3271, we're going to have 5 lectures or something on fasteners. And we're going to have, I think, 3 lectures on welds. And so you guys are going to get a lot more tools for doing analysis. But all of that learning next semester will be completely wasted unless you master these concepts of net tension, shear tear out, bearing, shear. Got it? Those checks for each structural joint or interface where we have fastened members. You need to be proficient at doing. The only piece of this that you're not going to do, and you're going to know, we're not checking shear tear out unless we're told in this class. We're not going to check bending unless we're told, and then all we're going to do is calculate the moment this semester. We're going to do shear and bearing a lot. And we also will sometimes do net tension if we're asked. Got it? Okay. That is our lecture on fasteners. Every single piece of this lecture is of immediate practical use for industry, structural, analysis. And you will see these ideas and get a chance to use them over and over and over again if you go into aerospace structures. Spend enough time on this, make sure you master it. The current video covers all this, and once I get this video up, it covers it even better, hopefully. Got it? That's all I got for you. Enjoy.